Good morning. Welcome to Class 10 of Emerging Technologies for Lifetime Learning. Okay. Today we'll continue our journey with picking off various very interesting area of emerging technologies and try to fit that within our various framework. For example, framework that has to do with anticipating consequence of new technology, checking the confluence when will a set of technologies and societal condition come together so that a dormant technology can become alive, so to speak. Okay, so as we have seen in many areas that we have discussed, and particularly today, there's some technologies that are based on maybe 15th, 16th century mathematics, right? So the mathematics is just waiting for the computational power. Maybe computational power plus mathematics is waiting for social atmosphere, or sort of like social phenomena to take off, and all together comes into a sort of like makes a long dormant piece of technology come alive and become ubiquitous. Okay, so a brief example I mentioned was like deep learning, which a lot of the mathematics was already well known by when I was a student. But the computational power, in particular massively parallel calculation of matrices, multiplication, matrices, manipulation, which today we take for granted because we have like very powerful game card, that wasn't available, right? And likewise, today I would even mention a piece of technology that I guess was available since World War II. Okay, today we'll discuss a little bit about radar technology and how, in particular, we are going to focus on how it developed into what's called synthetic aperture radar, and combine that with proliferation of satellites being launched, allow us to get a very precise imaging of the ground, not actual photo, but actually imaging that actually penetrates through clouds. And so even on a cloudy day, satellite can get a very precise image of the terrain and so forth. And we'll talk about how the social atmosphere has in particular in light of the Ukraine crisis and conflict, has made this kind of satellite observatory in almost real time, not quite, but very frequent updating of imagery, satellite imagery, taking photo from satellite and taking synthetic aperture radar imaging from satellite becomes very relevant, and it's not only available to scientists and engineers and the military. Now it's available to everyone. So what's happening is now ordinary citizen can help contribute to the war effort, even to make the what's called the fog of war less foggy. Okay, then there's a term in English called the fog of war, meaning that there's a lot of things that are uncertainty. You cannot really get absolute certainty when there's war. Certainly, like things like casualty counts, right? With pandemics, you can actually get down to individual cases. In fact, you can go to the daily COVID report and just count how many people have died since the pandemic began, down to the last person as of, say, reporting of yesterday. Okay, so maybe there's some lags there in data reporting, but anyway, you count individual. Okay, you can count individual. In war, you can't count individual deaths. So there's a lot of fog of war. There's claim and counterclaims. There's a claim that this side took out so many tanks and the other side say no, and so forth. Well, satellite imagery sometimes can settle all that. Okay, so clear some fog of war, so to speak. Okay, so we'll continue with that journey. But first order is today. We'll cover two things. So let me write that in the notes form. Okay. So today we have two topics: the cryptography and what I kind of mentioned just now, which is like a GPS technology, satellite, imagery, and GIS to an extent, yeah, obviously. Okay. I'm going to cover cryptography first because, for one thing, it's a continuation of last week. Recall last week lecture on Bitcoin and blockchain, right? Blockchain, and today we'll go over cryptography as emerging tech. Okay. Excuse me. Right. So let's do a little mini recall. What's a cryptographic hash function is? Okay. Well, key most attribute how is not invertible. Okay, call that. So we are going to discuss a few more functions before we go to that. So let's consider y is equal to f of x. Y is equal to f of x, right? Y is equal to f of x. That's called a function. You know that, right? So this is a argument or input. This is function. This is output. Fine. Okay. Now let's call inverse function. X is equal to f inverse y. Okay. Now, normally you say something like f inverse is notated like this, right? F minus 1. Okay, I'm using this note, so it doesn't have that. So f inverse or yeah. Okay, fine. If you have this as well as this, as well as can do this, then f is an invertible function. Okay, that's simple as that, right? So let's look at some very simple invert function. Okay, y is equal to 3x. Okay, then x is equal to y divided by 3. Well, that's easy. Oops, sorry. Well, that's simple enough, right? And that's invertible function. Okay, well, if hash is hash, hello. Okay, well, this obviously is x is a little bit more complicated. It's a text. Okay, let's do that. Okay, let's copy this number. Okay, cannot do hello is equal to H inverse of this number. Okay, you can't really find this. Okay, you can't really find the inverse. Now you can do pseudo inverse, right? You can do pseudo inverse. You can do pseudo inverse, i.e. keep guessing, yeah, whatever. A, B, C, D, E. Okay, let's say 5 later. Keep guessing A, B, C, D, E, A, etc. until you get this guy. Okay. Okay. And that's very hard. That's very hard. And that's, we call that, that's how that this difficulty computationally intensive procedure is what makes blockchain secure. That and plenty other thing is the basis. What makes. Okay, so that. Okay, so that's clear from last class. Okay, that should be clear from last class. So we have invertible function. Okay, that's a simple g y equals to 3x and x is equal to y divided by 3. Okay, so that's simple. Okay, that's simple. Now, so we have simple invertible function. We have non-invertible function, right? Function that cannot be inverted. You have, all you can do, you can keep guessing. You can do, all you can do is keep guessing. Okay. Now let's build something in between. Today we'll have something in between. In other words, f is, let's say, so in this case, okay, I can say that it's practically not invertible. Well, it's invertible, but it's in practice, theoretically as well as practically, right? Practically, it takes forever. Okay, so in other words, i.e. hash is practically, and in the way as well as theoretically, well, let's just say practically, not or not invertible. Okay. This difficult, that this is extremely difficult. There, let's do that. Okay. Okay. Right. So today we'll have another function. Okay. We'll call, so non-invertible or by the way, technical word for non-invertible is singular, but I'm not going to use that word very much today. Okay, it's not very intuitive. Okay, so how about this? How about this? F is practically not invertible to people without key, but easy to invert for anyone with key. Okay. Okay. That's so if we have something like this, well, it's in the word actually, right? I use the word key. That should be obvious, right? F is a lock. If F is practically not invertible to people without K. Okay, without K. And it's easy to invert find inverse of for anyone with K. Then F serves as a lock to which K is its key, right? Okay, now, okay, so let's think of this F versus this H, this function. Okay. Okay, so let's say on the one extreme, say you can look at my hand. On the one extreme, you have some function that's easy to go both way, right? From X it's easy to go to Y. From Y it's easy to come back to X. That's called invertible, and we can make it easy, right? You can make it as easy. And even if it's complicated with computer algorithm, it's easy. None of this takes more than a fraction of a second. Okay. Then on the other hand, you have a function that you get Y is equal to F of X very quickly, like hash function. But if you're given X, you can't get Y. No way. There's no way you can calculate Y. You can keep guessing, right? And if the combination of guess is combinatorially exploding, you can get to the point where even the most advanced parallel computer with gazillion dollars worth of GPU cannot calculate, because it's not a calculation. It's just a simple trial. Okay. So with Bitcoin and blockchain, they make it difficult. Okay. They make it difficult, but practically possible. Okay. Okay. So I should root something like practically not with cheap computer, but practically invertible with many GPUs. Okay, with let's say 90s computer, even, okay, 90s PC, okay, something like that. But practically invertible with many GPUs working, okay, running, but still not in seconds running. Okay. Okay, let's put that. Sorry, keep adding comment. But that's important. Okay, so on the one hand, you have a function so let us put on the scale. Okay, Y is equal to 3x. Okay, and then on the very far scale, you have something that absolutely, practically not invertible. In other words, this is something that that is not doable. No computer on earth can calculate. Okay, no computer on earth can calculate. So practice is basically theoretically not invertible, but also practically, because you cannot guess. Okay, so this function is theoretically not invertible, but you can do this. Practically, you can do it. Okay, if it's simple. Okay, if the hash is not that complicated, well, it's not the complication of the hash, but it's a combination of the how big the search space is. In this case, it's searching over a text of 5 letters, so it's actually what, 26 to the power 5. That's manageable. That's doable. Okay, so it's practically not doing, let's say practically by humanity. Okay, so that's it. Practically not invertible by humanity. So that's a little bit extreme. Invertible with many GPU. Okay, so we have this, right? We have this so far on a scale of difficulty. Trivial. Okay, trivially invertible, not invertible by humanity. Okay, not invertible by humanity. This would be like an example of solving something like, I'll just give you something that's outside the class, e.g. what's called traveling salesman problem with n over, I don't know how many cities. Maybe if you get beyond certain point, very large n. Okay, so that's definitely nobody, no computer, nowhere. Okay, you get all the computers in the world to work together, it still would take the age of the universe to solve. Okay, now we have this kind of Bitcoin mining. So it's invertible. In fact, let me write down pseudo but with many, okay, many GPUs. Okay, so basically big computers. Okay, so it's doable. It takes a while, even with many computers, and you can always make it more difficult. In fact, that's built in the Bitcoin protocol, that every 5 years or so, the number of zero that Bitcoin miner has to find gets added, something like that. Okay, so we have 3 scale difficulty: trivial, impossible, difficult. Okay, difficult. Now, I'm going to add another layer of difficulty over here. I'm going to call it virtually impossible. Virtually impossible by any one entity. In other words, maybe if you bring all the humanities together, right, and you run it for days, you can find it. But it's virtually impossible if any company, any Bitcoin mining operations, no matter how large it is, it's basically impossible. Virtually impossible. Okay. Now this one is not very useful. This one is not very useful. But there's one class of function that's useful. It's virtually impossible by any one entity without key. Okay, implicitly, but doable with, perfectly doable. Okay, so now we have, let's say, a degree of difficulty. Okay. I'm gonna put this guy over here. Okay. Maybe not. Okay. Here we go. Yeah. Sorry about that. Okay. Okay. So this is not doable. Trivially doable. Pseudo invertible, doable, but with many GPU. Okay. This one is virtually impossible. But if you had a key, okay. So last class, the whole of Bitcoin technology is built on this class of function. So that's the mathematics, okay? I'm not giving you the details of mathematics now, but I'm giving you the intuition, okay? So there's some function that is guessable, but takes a lot of computer. And then there's function that's not even guessable with all the computer. And there's function that's, in theory, if you take the whole world to calculate, it's doable, okay? But virtually it's not possible without key, okay? You can even say something like not invertible by humanity without key. You can put that in there as well, but you know, I'm just being a little bit more generous. Okay, fine. So let's have this kind of concept. So this function is used for hash. Hash. Crypto. Hash. Okay, that we saw in Bitcoin mining. Okay. Bitcoin mining. Okay. Right. Okay. So we're going to talk about this today. Virtually impossible by anyone without key. So if F, we want this. F is practically not invertible without key. So let's copy that. Okay, so this is what we talked about today, last week, today. EC2 inverse or relatively diffuse, relatively. You still need computer, by the way. Okay. Then F serves as a lock to which key is key. Okay, so that's this. Okay. So what's the difference between this? Encrypt. This is called encryption. To lock secret with mathematics. It's called encryption. Okay, so this is hashing. This is encryption, right? Hashing, you definitely are not going to invert it. Encryption, you could invert it. You can invert it with all the helps of everybody, you know, very big computer running for months, or you can do it in minutes or seconds if you had the key. So if you have this kind of thing, it's called encryption. Okay, encryption. So now, this, what's good about encryption? Well, this is encryption has been around. Remember this thing I told you about thinking of technology, like what happened to the society and how long it has evolved? Well, encryption has been around since, God knows, Roman time, at least. Okay. In fact, there's this thing called Caesar cipher. Let's go to internet. Caesar cipher. Okay. Caesar cipher. Rahat Caesar. Okay, that's in Thai. That's not fair. Okay. So why is it called Caesar cipher? It's because it's used by Julius Caesar, right? Who is a Caesar who, when did he live? 100 years around, anyway, around, okay? I think this is, yeah, I think this is precise. So it was before Christ. So 100 year BC to 44 year BC. So he lived about 45 years until, you know, his colleagues decided to get rid of him with some kind of stabbing action. Right. So anyway, okay. Okay. So encryption has been around, but why has it taken off? Well, this is where internet come in. Okay. So two things happen. Now, Caesar used this because what? Because he was doing a lot of war. Okay, Caesar was a conqueror, one of those guys who likes to enlarge the empire. So he needed that secure communication to his general. So the reason was war. Okay, and that reason all the way to World War II. Okay, in fact, all the way to any kind of war. So that's nothing new. Okay. Same all the way okay. The reason was war. Fine. So what's new? Anybody? Anybody? Well, what's new was internet. Internet, right? So now it's not you communicating a secret invasion plan to your general, but you sending a picture to your friend, to your grandma, right? So it's a baby picture of you. You don't want anybody else to see a baby picture of you. You send a baby picture of you to your grandma. Okay. So now that's it. That's what so the need for secrecy used to be part of, you know, the war making effort, but now it's just part of ordinary life, right? So e.g. sending baby pics, okay, and also making payment, right? Okay, so let's go to any kind of website. You would see that there's a little s here. Notice that? Okay, you notice that little s here? That s is basically saying that this website has been secured to some kind of encryption. Okay, so when I was a student, we just had HTTP, hypertext transmission protocol. Okay, but that's not secure. That's sort of like plain text. So when you add s, there's a little s, you notice. Okay, so even if I did this, it's going to go to s, because the server will say I'm going to go to the secure channel. So that little s is everything we're talking about today. Okay, so that s, okay, that s is very important. So that s is for encryption. Hence, HTTP becomes HTTPS. Okay. What does it? So what's the S? What is the S behind HTTPS? Okay. Stand for secure. Okay. So that's what's important. Now, if I click on this, presumably it's going to mention something like what we are going to talk about now. Okay, that's not useful. Okay, right. So now let's talk about encryption. So encryption is one of these things, right? Virtually impossible by anyone without key. So we always have, and by the way, in encryption, there's always three people. Okay, there's Alice, Bob, and Eve. Okay, and Alice and Bob try to communicate in secret knowing if wants to eavesdrop. Get it? that's why the third person is always Eve, because she likes to eavesdrop. That's the definition of eavesdrop. Eavesdrop. Oh, there's an S. Sorry. Okay, so that's why this character. Let's introduce three characters. Let's introduce three. Okay, so that's it. That's a basic setup. That's a basic setup. Okay, that's a basic setup. Now, if Alice and Bob, okay, met in person, they can exchange secret key. Now, I'm going to talk about key in a physical sense now, right? But it's the same thing as handing over a piece of paper. So a secret key could be some number. Okay, secret key. In fact, let's make up one number. Let's make up like a secret key. Let's make that's my, oops, sorry. Okay, 3127. Okay, 3127. 3127. Okay, that's my favorite key. Okay, right now you can hide message. You can hide message. Okay, I'll talk to you about how difficult it is. But I want to create a setting. Okay, so there are three situations. Set up. If Alice and Bob met in person, they could exchange free. Okay, so number. Okay, if Alice and Bob, okay, if never could not meet. Okay, let's say could meet. Could not meet in person. They must send the key over the internet. Okay, problem. Eve has internet. Okay, so Eve can basically crack. Okay, so this is assume. Encryption doesn't mean that you might. Okay, let me write that down. Encryption isn't just not letting people use your computer. Okay, so this is sort of like, even if they use computer, they come in and use your computer, right? Alice sends Bob, and Eve comes in and use Alice's computer or Bob's computer. Can see the message. Okay, now technically Eve would not be using Alice and Bob, but would be hacking it. Okay, so this is more, it's got to be more secure than that. Even if it's hacked, gets all the information, you still cannot read it. So that's important. Okay, it's a locked message. Okay, so this, okay, has a problem. That's a problem. Okay, on the other hand, if Alice and Bob could not meet in person and they don't even trust each other for all message. Okay, so that's even more important. That's a little bit more impersonal. In other words, there's a specific message that Bob and Alice want to share. Okay, but Bob and Alice are not perfectly transparent to each other. So they don't want to share every message. They just want to share just one message. Okay, something like that. So these are the setup. Okay, so this is something that the Roman general, okay, I think in a way all the way up to World War II used. Okay, so in World War II, World War III, World War II, there were like secret code book. Well, it's not quite simple as that. It's sort of like procedure that gets handed in physical book form to say a submarine commander or something like that, so that they can be used to uncrack to open the message. Okay. By the way, a locked message is called cipher. That's why this is word. Cipher encrypt message. Okay, sorry. Okay, so basically you get a message. So you get a message. Okay, and then you go cipher. Go to encrypt message. And then you go to original message decrypt cipher. Okay, that's how it works. Okay, that's how it works. So Caesar makes a message. He used his encryption method to do a cipher. That's called Caesar cipher. Send it to his general. His general takes this message, this cipher, and decrypt it. But he uses key. Secret key. Okay, secret key. So at some point before Caesar's general goes to war, Caesar hands him maybe like a piece of paper or something. Okay, some kind of instruction. Okay, so that situation is here. Alice is Caesar. Bob is a general, a Roman general. Okay, same with World War II. Okay, so all this has been operating in World War II. Now, what about, and that works fine, right? Because military is good at keeping command and control structures, so you can meet in secret. But it wouldn't work with the internet, right? Because you wouldn't want to say something like, if I want to send a secret bank account because I want to order things from Amazon, right? I don't want to fly into to United States, go to Amazon headquarters and hand over a piece of paper that has my bank account, or a secret that can open my bank account. And I don't want to, and so I have to send this instruction over the internet. And also, I don't want this instruction to be used all the time, right? I want this instruction to be only used for just that time I'm buying that book from Amazon, right? I don't want Amazon to have to be able to well, maybe Amazon is it's not a good example because it's a big corporation, so it can't steal from you. But let's say some kind of peer-to-peer transaction, right? Just buying B&B or whatever. Okay. So you want something that is doable between people who haven't met, right? And there's no mechanism, there's no military command and control structure that can control this kind of handing over the message. So this is doable. Doable. So this is doable up to World War II, and this is after World War II. So I want to do this. Okay, so all this happened after World War II. Okay, all this is able to be done. Okay, so in other words, even if the warring party intercept the message, can't crack it. Can't crack it. Okay. So this is what happened. This is what we're going to study today. So encryption technologies only came alive, okay, because, well, the basic mathematics is here, okay, and basic mathematics, but there are more mathematics that's developed. And this is very important. Okay, fine. So this, in a way, Okay, there are three stages. Okay, three stages. This one is share key, right? These two. Okay, share key. Okay, so Alice and Bob would have no secret from each other from that point. Okay, but here they still have some secret from each other. So let's see how we can address this. Okay, how we can address this. Okay, fine. So let's go to cryptography proper. Okay, so so again, let me recall, right? Last week we have invertible function. Now we're talking about function, not invertible function. So we're talking about function that serve as a lock, as a key, right? And so encryption has been around, and now we're going to talk about modern day. So like after World War II. So I've set all the stage. Now, World War II. Okay, so after World War II, and later on with internet. Okay, so now we've got this. Okay, fine. So let's think of a function that is hard to do if you don't have a key. Okay, and easy to do if you did. Okay, let's think of this. Okay, let's think of a function. Let's find this function. What kind of mathematical function makes good lock? Okay, now I have to introduce you to what's called clock arithmetic. Okay, clock arithmetics. Okay, so if you put this in the internet, you will see another word that's called modular. Okay, clock arithmetic. Oops. Okay, clock arithmetic will bring you to the word modular arithmetic. Okay, so I'm gonna say clock arithmetic. Proper word. Okay, so a clock has 12 numbers, right? So you can only display 12 numbers. Okay, how do you display 13? Okay, you wrap 13 around the clock and display 1, right? Okay, so right away you can see something that's very easy to do and very hard to find the inverse. For example, if I have this number, okay, if I have this number, okay, and I wrap around a clock. Now, let me add another notion. Let this clock have prime number. You know what a prime number is, right? A number that have 17 numbers. Okay. Yeah. Note, 17 is a prime number. Okay. A prime number is a number that you cannot break down. Okay. It's prime. Okay. So for example, if I go to here, I say prime Q, okay, 7, yes, it cannot break down, okay? But if I write some number, big number, and I say false, in other words, this number can be divided, at least, well, obviously it can be divided by 2, by integer, right? So number that's integer divisible is not a prime. Well, you say, what about this? So this looks like a big number, right? But actually, this actually breaks down. It's breakdown. I don't know what the breakdown is, but it's breakdown. It's breakable. Okay. So, but some number like, well, 2, 2, 1, 1. Okay, it's true because even though it's much smaller, you cannot find any number that multiply any integer. Okay, so a prime number is prime number. Okay, cannot find 2 integer that multiply to 7. Okay, so let's do this. Now in Mathematica, you can do along with this because everybody has a Mathematica, right? Type the word mod. Okay, don't pay attention to above. We'll get to that soon enough. Mod. Okay, mod. And type this number, right? Around 17. 0. So you know that this thing wraps around 17, a clock that has a 17 number. You can do it so many times and you get number 0. So you know that this thing is perfectly divisible. Okay, that's it, right? So you take this number as a string, right? And then you have a clock. Think of it as a string. Think of this as a wheel that is 17 inches in diameter. Oh, sorry, in circumference. Okay, so this is a string. Okay, so take a string of length, say inches, and wrap it around a clock with 17 inches in diameter. Same thing. Okay. Okay. You can do this. You can do this how many times this time? Okay. Now let me change the number a little bit. Let me add 5 to this. Okay. Let me add 7 to it. Okay. Let me add 7 to it. So let me add 7 to it. Okay. Right. What's happening is that it's going to wrap around this clock this many times and then has a leftover of 7. So modular arithmetic is like finding the leftover, basically. Okay, you can do this any time and get leftover. Okay. All right. Now, why is this a perfect example to make good log? Because you can do this. I can do this, right? I can take this number, wrap it many times and get 7. Okay, that's easy. Okay. In fact, how do I do it in general? Okay. If you didn't have this function, okay, you didn't have this function, you want to do it by hand, how do you do it? Anybody? Well, you do this, right? You do this, right? Okay. Okay. Well, I'm making the number too big. Okay. So this is some number with some decimal. Okay. Right. So basically, what you want to do is round this down. Okay. So let me make a new example. Okay. There. That's a little bit more manageable, right? So this string wraps around a clock of diameter 17. Okay. So many times. Okay. How many times? You use that in your calculator. Okay. So it can wrap it around it 25 times and get this leftover. Well, basically, you just take this leftover and you divide by, oops, sorry, multiply, not divide. Okay, well, there's some numerical thing here, but basically this is 14. So you can get this number. Okay, so you can see that this is easy to do. Okay, so it's easy, okay, to use. I'm going back to original number. Do this. 2. Okay, it's easy to do this, relatively easy to. Very hard to find inverse of this. Okay, in other words, I give you 17. Oh, sorry, this is equal to what? 7, right? Very hard to find this from 7. Okay, in fact, you don't know. Okay, there's some other condition that so you can't really find this. So basically, this is not doable. Okay, it's not doable. So that's it. That's it. That's the essence of encryption. Okay, so the essence of encryption is just that. Okay, so encryption is done this way. Okay, so first you translate your message into some kind of ASCII number, right? And then take that number and you wrap around this, and it's impossible. Well, it's hard to do. Okay, now here's a problem. Okay, here's a problem. Okay, here's a problem. First of all, you have to be able to decode it. Okay, first of all, you have to be able to decode it. Okay, now let's just say that even if it's hard to do, okay, if it's hard to do, okay, you can still find it because you have a key. So that's the essence of having a key. Okay, so there are two problems. Okay, two problems. Let's go with this one first. Okay, so if you had a key, so something like this is but the mathematical lock is not just modular arithmetic. Okay, so there's a whole there's a few more steps to do it. I'm not going to cover it today, but just to show you that this is something that's very good. Okay, so oops, so you see this now. So let's assume you had, okay, you had a way, you had a lock and key combination. Assume that you have a lock and key combination. How do you send the key over the internet? Okay, how do you send the key over the internet? Okay, and this is where technology number 1. Okay, I'm just going to say tech number 1. Okay, it's all emerging tech because of the application, but tech number 1 is called Diffie-Hellman key exchange protocol. Okay, Diffie-Hellman, and I think there should be a Wikipedia page on it. There it is, Diffie-Hellman algorithm. Okay, It's very easy. It's very easy. Oops. Okay. Okay. Bob, Alice thinks of a number. Okay. A secret number. Okay. Okay. Okay, Alice. Bob thinks of a secret number. Okay, Bob. Okay. Okay, and this is very clever. This is very clever. Okay. Alice thinks of a creep, and she doesn't share this, not even to Bob, by the way. Okay, not even to Bob, not even to Bob. So it gets to the thing where they don't trust each other for a message, and there. Thinks of a secret number. Okay, thinks of a number. Bob thinks of a secret number. Okay, there's a public available number called set of number called basis. Okay, just some number. Okay, say parameter. Parameter public. Okay, so this could be one number, could be a few number. In fact, it's a public available set of numbers. Oh. Okay, so we have this thing now. Okay. Okay, so Alice doesn't send the secret. Alice applies the secret to something that's already in public. And then she sends something like Alice uses, okay, K Alice to lock something from here. Okay. So lock something from there. And then this becomes, and then gets cipher Alice. Okay, this is very good. Okay, so now, okay, nobody knows what this is. Bob does the same thing. Okay. Okay. Now, Alice sends Bob this thing. Bob sends Alice this. If gets both, okay, but cannot do anything. And meanwhile, okay, meanwhile, so now Alice uses K Alice to lock Cyber Bob. Okay, and likewise, Bob use K Bob to lock Alice. Okay, Bob, sorry. Oops. Okay, notice nobody trusts anyone. Nobody trusts Alice doesn't trust Bob. Bob doesn't trust Alice. Nobody trusts Eve, right? But you get something. Okay, so it turns out this, when you lock, when you take some number, okay, some number from this, and you lock by Bob, and then you lock again with Alice, versus when you lock by Alice and then lock by Bob, it turned out to be the same thing. Okay, so let's call it cipher Alice on cipher Bob. Okay, whereas this thing, you get cipher Bob on cipher Alice. Okay, nice. But because locking is commutative, i.e. f of g of x is equal to g of f of x. Okay, it's commutative. Because of this, this thing is equal to this thing. Okay, and we call it share key. Alice. Bob. Okay. This is very important. Okay, this is very important. Notice in this narrative, has anybody trusted anyone yet? No, nobody trusts anyone. No one trusts anyone. So this is called Diffie-Hellman key exchange protocol, right? What happened is that now you can use this as a key. So it's a key that's generated for the job. So it's achieved this thing. Alice and Bob never met, could not meet in person, and they don't even trust each other for all message. Okay, just this one. Okay, and in fact, in this one, they don't even so they don't. Bob doesn't know key Alice. Alice doesn't know key Bob. Nobody knows, but they have a shared key. So just this once, all right? This once they have a key. So now they can send any kind of encryption. So now Bob and Alice and Bob can now send cipher to each other. Locked with, not with K Alice, not with K Bob. So I'm gonna call it K Alice Bob. Okay, that's perfect. So now we have perfect. Now this is symmetric. Okay, this is symmetric because Alice and Bob has this key. So this key, note how this key is symmetric, i.e. Alice sends Bob, let's say Alice is sending Bob message, okay? So you use the same key, i.e. same key will now be used by sender to encrypt and by receiver to decrypt from now. Okay, so that's it. Okay, so technology, well, actually, let's say technology number one is encryption function. I haven't, based on clock modular clock arithmetic. Okay, that's technology number one. Technology number two, you can share a key. Okay, so this technology is i.e. available available for a long time. Okay, so this is only available after World War II. Okay, so that's been available for a while. This is available after World War II. Okay, so that's one thing. So now Alice and Bob can do this. Now the function to do it, and I'm going to send you a Mathematica to play with, is this guy. Okay, this is called Diffie-Hellman Okay, doesn't matter. Okay, I'm just gonna send some number. Okay, I'm selecting that. Okay, now these are parameters that I mentioned about. Okay, this is this thing here, some kind of public parameter. Okay, so this is something that everybody knows. Okay, so it's not just one number, it's two numbers, doesn't matter. Okay, and Alice thinks of a secret number. This number is not shown to anyone. Bob doesn't know this, Alice doesn't know this, and this is Bob's secret number. Okay, so this is I'm playing around with this. Okay, so this is a demonstrator. Now encrypt this. So this is K Alice, this is K Bob. This is the function. The function is to take the message, okay? To take this number G 279. I don't know if I'm making this as large as I think possible. Okay, this is a public number, right? Put this public number, put it over here. Okay, put this public number, put over here, and raise it to the secret number, which is 1, 2, 3, 4. Okay, so this is the encryption. This is the encryption. Okay, so take this public number, take this public number, raise it to a secret number by Alice, wrap it around. Okay, so this will be something like take number G 279, raise to the power 1, 2, 3, 4, wrap it around the clock of circumference P, and find the remainder. That's what this notation means, modular. Okay, so the same word, modular arithmetic. Okay, Bob does the same thing, takes a public number G 279, raise to his secret number 7531. Okay, wrap it around the clock of diameter, of circumference 557. Okay, 557. Okay, and gets a number. This number is the cipher 537. Send this over the internet. Okay, Eve knows his number, knows all this, but doesn't know this, does not know this, cannot crack it. Okay, now once Alice has Bob's number, takes Bob's number, put it here instead. Okay, originally it was a public, right? Put 279. Now put Bob's number in here. Put Bob's number here. Again, use the private key to the power A. So basically what's happening is that G raised to the power A and to the power B. It's the same thing as G raised to the power B and to the power A. So they get the common number. This is very important. Now they can use this as a key. Okay, this is Diffie-Hellman key exchange protocol. And this is used up to today. And in fact, the military, NSA, whatever, you know, FBI, CIA, you guys, everybody sending things on the internet at some point will involve this kind of algorithm. Okay, now obviously the number will be a little bit bigger. Okay, but this is a Diffie-Hellman exchange. Now you and Amazon, Bob and Alice, a general and his commander, doesn't matter, you and your grandmother can keep sending stuff back and forth, 1,000 times using this key, and nobody will be able to crack it virtually. Okay, it's impractical. So now that you have this number, but the beauty of this thing is this: Alice and Bob has a shared secret, and yet part of the secret neither one knows. So Alice doesn't know this number of Bob, Bob doesn't know this number of Alice, but together they can create a shared secret, and this shared secret can be thrown away. So Bob and Alice doesn't have to trust each other for eternity. It can Bob and Alice can only trust each other just as long as you use this. Okay, so it's a very cheap, inexpensive way of locking, and you don't have to you don't have to have a secret between you don't have to share a secret forever, right? So you can be Alice, Bob can be Amazon, right? Once you share this, okay, once you share this, you still don't have to share any other secret with Amazon. And Amazon certainly is not going to share any other secret with you, right? So this is sort of like a disposable lock machine. Okay, so this is kind of a locking mechanism that's very disposable. Okay, so this is the technology number one. Okay, and you would use this, by the way, with every transaction, including blockchain, including Bitcoin transaction. That's, you know, you need some kind of encryption. Okay, so this is what's called a Diffie-Hellman key exchange. Okay, so what does this rely on? This rely on the fact that basically relies on, okay, so you have something like this function. So yeah, this function. Basically what's happening is this: you rely on this function, this A. Okay, that's it. That's it. That's what it relies on. Okay, so this modular distribution, well, actually, if I write this, are you surprised? Yeah. Okay, this you're not surprised, right? 3 to the power 2 to the power 7 is the same thing as 3 to the power 7 to the power 2. But what is so cool about modular arithmetic is, even if you did this, okay, this is the same thing. What you were doing is actually not that, but this. Okay, let me show you. There. Okay, that's what you were doing. Okay, that's what. So Alice encodes the thing, locks it. Bob locks it. It's the same thing as Bob locks it first, and then Alice locks it. So in other words, this is the same thing. Okay. Okay. Now in Mathematica, it's written something like mod A to the power B C. Okay. And then, okay, well, obviously that's equal to this. True. Okay, that's obviously true, right? But what I want to say is that sorry, G. Okay, and this A. I don't know if I can do this, the notation. Okay, so maybe I should do something like this. Okay, something like that. Okay, so even though the modular function is, so that's like God's gift to encryption, because this modular, this arithmetic, right? It's practically not invertible. You can't crack it, and yet it has a very nice property that's commutative, right? So now, okay, you can lock things twice and get the same result. Doesn't matter which order you lock things in. That's what it means. Okay, so this is it. Okay, right now, what if? So that's a problem. Okay, what if you don't want to share, okay, secret with so let's say what if you want people, anyone, to be able to send you secret? Okay, now notice this is very even though it's used only once, it's very cheap, it's still very symmetric, right? You and Bob kind of like have the same thing. Now let's say it's not you and Bob. Let's say you are a website, website want people to send you their secret. Okay, their secrets, right? Now here, why? Because you're not trying to send any secret back to them, right? You don't want to exchange, so you don't want, i.e. you don't want to exchange. Okay, just get one-way. Okay, one-way message. Okay, wouldn't it be easier? Okay, instead of doing all this, you can just send them logs. Okay, that's it, right? So this is a different, this is note how this relationship is asymmetric. Okay, because you're sending, now you don't have to go through Diffie-Hellman exchange protocol whatsoever. Now you can just say, you could just send logs, okay, to anyone. Okay, doesn't matter who, Alice, Bob, I don't care. The point is that even if they intercept, they can't do anything because it's a log. It's not a key. Okay. Now, confusingly, now pay attention to this. Confusingly, in cryptography, this log, they still use the word key. So I apologize. I can't make life any simpler. But when you go and study on your own cryptography, or you go to blockchain site, they're gonna talk about. So from now on, a log is known as private key. Sorry, a key, public key. Okay, from now on, okay, and this is very important, and just live with it. There's nothing I can do. And a key is known as private key. Okay. Okay. From now on. Okay, that's it. So this is technology number 3. RSA. Technologies RSA. What does RSA stand for? Well, RSA is the name. Actually, you know what? I'll tell you a story. Well, not a story. It is true. RSA stands for these guys. Okay? But actually, historically, they did not invent this. Somebody else invented this, but made it a secret. So it was discovered later. Now, these 3 people discovered it and published it as an academic, I think. So that's why it was named after this. Some guy working for U.S. intelligence, I don't know, somebody probably invented something like this, but it was complete secret. It wasn't an academic work, so doesn't get the name for it. To this day, I still don't know who that person is, but I know that it was some guy or a team of people. Okay, so this is called public key, aka asymmetric encryption scheme. Okay, so you guys know this. Okay. So you have this thing, right? You have this oops. I'll show this. Where was that demonstration, that little function? Where did I hide it? Okay, yeah, this thing. Okay. So mathematically, it's well, I use a like this. It's okay. So you know this, right? You know this. Okay. Unfortunately, I can't write this in the LaTeX, so I have in text, so I have to write it. So this thing is the same thing. So private key, share key equal to this. Okay. So that's Diffie-Hellman. Okay. So with I want to write in here, but I can't, do the exponential. So this is, I'm going to write it in here. So share key is this. Okay. So Alice locks it, Bob locks it, Bob locks it, Alice locks it, and the whole double lock becomes a key. Okay, becomes a key. So now this symmetric key. Okay. Now think of another process. Okay. Think of another process where this, okay, so this is a symmetric key. I want another process. I want something like this. I want a message. Okay. Now it's not. Now this is not just some number. Okay, some message, some kind of M message. Okay, and I want to be able to do this. Okay, what it means is that, but these two operation, okay, these two operation kind of like undo itself. If I can do this, I can say private public key. Okay, so remember, public key is a lock. Okay, public key is a lock. So maybe I should put down lock for now. Okay, so this is, anybody can send you this. Anybody. This is your customer. Your customer send you this. Now each customer sends his own secret message. Nobody else knows. Okay. You want to know, right? Because you want to get everybody's secret. So this is how a payment can be made, right? So a customer sends you an M. This guy sends you an M. Okay, message. Now what you want to do is have this lock be public. And then you can do another operation called unlock. And then you get M. Now, obviously, in this case, a lock function is called public key. An unlock function is called private key. Okay, that's it. That's what this means. Okay, and why is this difficult? Why is difficult? Because public key is product of two large prime number. Okay, so remember this. Okay, so in this case, public key is product of two large prime numbers. Okay. Private key derive from knowing that two large prime number. Okay. In fact, private key is the two large prime number. Okay. Now, how would I do this? How would I do this? And this is an example number 2 that I created for you guys to play with. Okay. Ta-da. And this is called RSA. Okay, it's RSA. Okay. Now, the way it's done is this. Okay. So this is something. Okay. This is a prime number, right? It's okay. So this is kind of like what happened. You have this prime number, and you have this prime number. Okay, that's this one, that one. Okay, this is secret. Okay, so this is 283. This is a prime number. 251. This is a prime number. You can check. You can check here. Prime Q. Is it prime number? True, it is prime number. And is this one a prime number as well? Yes. Okay, they're both prime number. Good. Okay. Now, in theory, this can be very large. Okay, and the one that's used by the internet, the one that's used by NSA, the one that you say you need quantum computing to crack, has a very big number. Okay, so this is not large, but I'm saying it's large. Okay, in theory, it's large. Now, the private key are the two large number. Yeah, so it's derived from the two, so it's actually, you know, okay, right? So you have two large prime number. Large prime number. What you do is you multiply them together. Multiply them together. Okay, multiply them together. So I multiply this number together, and I send it over the internet. Send it over the internet. Okay, this internet number anybody can use to log. So this is my thing here. Okay, this is my number here. Public key, anyone that can use to log. Now, the private key, okay, the private key is sort of like something that multiplies it and undoes it. So basically, it's kind of like an inverse. It's kind of like an inverse. Okay, that requires a lot of mathematics, but basically I have it. The reason I have it is, and I'm going to just take 5 minutes to describe this. There's something called this one, Totient number. Totient number. Totient number is really weird. Totient number. Totient number. Okay, Totient number is number of, okay, number of number less, number of number less than, so totient of x is number of number less than x. That is co-prime with x. In other words, it doesn't share any common denominator. Okay, so what's 8? 8 is equal to 2 times 3. Oh, sorry, 2 times 2 times 2, right? Right. So, what's number less than 8? Okay, number less than 8. Number less than 8 is what? 1, 2, 3, 4, 5, 6, 7, right? That's number less than 8. Okay, number less than x. Okay, so 8. What's the number less than x? 1, 2, 3, 4, 5. Which one of that? Okay, which one of that is co-prime with 8? In other words, it doesn't share any prime. 2, right? share number 2 with 8, 4 share with 8, 6 share with 8, 1 doesn't, 3 doesn't, 5 doesn't, 7 doesn't. So that's, in other words, quotient of 8, okay, quotient of 8, which is called Euler phi, is 4, okay, 4. So you start with number 8, you look back, and you count the number that's co-prime. Now, if you actually have, what about Euler of, well, 7, okay? Okay. How many numbers co-prime? In other words, you can't co-divide this thing. So 1, 3, yeah, 2, 3. So actually, Euler of phi is equal to 6, or 7 minus 1, right? Right? What it means is this. This is a very important thing. Euler phi okay. So Euler phi of number count the numbers less than x that is co-prime with x. So when x is prime, okay, Euler phi, it's called quotient of x, okay. This is name, okay. So you can actually say quotient or Euler phi, okay. When x is prime, Euler phi is equal to x minus 1, right? X minus 1. So here's a trick. Here's a trick. Let's go back to this demonstration. Here's a trick. I have two prime number, right? I need to know, okay, the function that would undo this. The function that would undo this. Okay. So the function that would undo this, private key. Okay. So private key is derived from this. Euler phi of public key. Okay. Now, you need to know two things. This, okay, and also in general, okay, Euler phi of P1 times P2 is equal to Euler phi of P1 times Euler phi of P2. Okay, so maybe I put N here. Okay. So when N is prime, now let's use P from here, because you P for prime, that's the traditional way. Okay, in general, this is true. Okay, in general, this is true. Okay, so it doesn't even have to be prime. Okay, but it's so what happened? You calculate. Okay, so public key is a product of large prime number P1 times P2. Okay, Euler P I try to remember. Would you guys get confused if I write x here? What I mean is multiply, okay? P1 times P2, okay? Hopefully, okay, right. So what happened is this. It's derived from, in fact, how is it derived from? It's derived from Euler, derived from Euler phi of P1, P2. That's the deal, okay? Now, so the public key is equal to this. The private key is derived from this, okay? Now, this is where you always say cryptography is based on large prime factorization. That's what you hear in internet, whatever. This is what it means, okay? You have this number, which is prime. You have this number, which is prime, okay? You multiply together, okay? And you call it n, okay? N is equal to P1 times P2, okay? N is equal to 1. You don't show P1, you don't show P2, you show n. You keep, so this basically is a public key. This is your private key. Why? Because if you know this, you can do this. Right? Right? Okay. It's Euler P1, P2 is equal to Euler P1 times Euler P2, which is equal to P1 minus 1. Okay, this is not factorial. Okay. And then P2 minus 2. Okay. So this is what it's meant. Okay. If you have n, you don't know that it's made out of two numbers. You just know n. The secret holder knows P1 and P2. Because this thing, because he knows P1 or P2, he can calculate P1 minus 1, P2 minus 1, which is gives you this Euler P1 and Euler P2, which is Euler P1 of P2, which is Euler of n. Right? So now life is simple. Okay, life is simple. Okay, now we have this. This sometimes you hear as a word trapdoor function. So now you have something. Okay, now there's a little bit formula to it. There's a bit of a formula to this. Okay, so you have to multiply something, but basically it's some kind of something that involves Euler phi of public key, which you do, okay, because you know that this thing breaks down easy. Okay, so that's it. That's how this is how the whole thing works. Okay, so this is the essence of Diffie-Hellman key exchange. This is the essence of something. Okay, so let's say something like this. Okay, some kind of a bit more calculation, but doable calculation with this. There. If you understood these two concepts, you understand all of modern cryptography. Okay, this is Diffie-Hellman. I want two people to share a secret. Part of it is constructed from individual secret. A has a secret, B has a secret, but the secret of B and A are commutable, right? So when A locks it, send it to B, B locks it again. So same thing as B locks it and A locks it. Think of it as a secret food ingredient, right? Except in cooking, if you fry before you bake, it's not the same thing as baking before you fry, right? But this case is commutable. So this is called Diffie-Hellman key exchange. That's the most fundamental. If you understand this equation, you understand modern encryption. Okay, one modern encryption. This is symmetric way of exchanging key. But once you have this, you can use encryption. Okay, where the lock and the key is the same thing. This is called public key cryptography. You send a public key to the person, okay, and the person, okay, does this public key. Okay, message is a cipher. Okay, and you take the cipher. Okay, so basically it's sort of like this. You take a cipher and you unlock it. So what happened is the original message gets public key locked, gets unlocked with something that involves Euler phi of public key. Euler phi of public key depends on knowing what the prime breakdown of public key is. In fact, if you knew it, it's easy. If you don't know it, it's very difficult. Okay, so that's the explanation for totient. Okay. Okay, that's it. So now you have two things. You have two things that, let me show you how it works. How it works is here. Right? Okay. You pick a prime number, P1. You pick a prime number, P2. In this case, I write Q. So that's your thing. All right. You know that this is a prime, so that the Euler phi of phi, okay, which is the Euler of the product of this thing, is the Euler phi of this and Euler phi of that, which turns out simple. It's just that 283 minus 1 and 250 minus 1. So 282 multiplied by 250. So that's your thing. So that's going to be used to uncrack. Okay. So now this is some public parameter. Okay. Right. So this is the message. Okay. The message gets encrypted with this. Message encrypt with a public key. You get this. Okay. And then you get encrypted message to the D with this. Okay. So this would look then as the same thing as the step we did earlier, which is to say cipher private key is equal to message. Okay. So so you can think of two steps or you can think of one step. Okay. Okay, this is Diffie-Hellman key exchange. Okay, so that's Diffie-Hellman key exchange. Diffie-Hellman Hellman, okay, and this one is RSA. Okay, RSA is you public key. The person wants to send you something, say payment instruction, raise to the power public key, mod P, send this over the internet. You take this over the internet, you raise it to power public key. Okay, so it's a bit like that, right? It's a little bit like that. So you can say, instead of getting this, in other words, message public key and then private key. Oops. Anybody notice private key is equal to message. Okay, so it's a slightly different thing from Diffie-Hellman as in. In Diffie-Hellman, you lock things twice. You don't get the original thing because the original thing is actually public. You don't care. Okay, so you get something that is a shared secret by locking things twice in different order. In RSA, you care about the message. So maybe I should message. Okay. Oops. Secret message. Okay. Secret message locked with the public key. Mod P is equal to encrypt. Okay. Encrypted private key is equal to. In other words, this. Okay. Now that looks better. Okay. So this thing is the difficult bit. Is some kind of calculation that requires this. But once you calculate this, okay. So I should put just say private key. Private key based on derived from. Okay. Now maybe this is a better way of writing. Okay. Okay. So that's it. Right. Again, if you want two parties to share something, okay, and they're going to use it once or twice or whatever, okay, you just get some public number, Alice locks it, Bob locks it. Bob locks it, Alice locks it. They both have. Okay, so this is a share key, symmetric key. Now use this to do whatever you want. But in this case, okay, in this case, you want a key to be a lock to be available publicly. Okay, so anyone can send a secret message by locking it using public key. Again, public key is the lock. Get an encrypted message. Okay. You take the encrypted message, you raise it to power private key, and you get the secret original message. Okay, but it's very important that private key is derived from knowing this. Okay, and if this is the product of large prime number, nobody can figure that out. This is the key, and then you can just end it. Okay, so you take the encrypted message, secret message. Okay, sorry, you take the, yeah, that's right. You take the encrypt message, private key, secret message. So secret message. Okay, so these are the most important thing. Okay, these are the most. I'm taking you through all the logic. If you go to like some tutorial that teach you how to use this, it won't tell you any kind of logic. You won't understand why this works. Okay, why it will not work. So note, if quantum computing can take n and find out p1 and P2, then RSA is cracked. That's it. Yeah. This is what it means by quantum cracking. Okay, if a quantum, because quantum can search multiple value at once, right? Quote unquote, searching multiple by superposition. So we talk about that. So these are the three technology set that is very important. Okay. Right. So now you have three pieces of technology that that you understand. So you have a generic way of locking things. Okay. So I actually didn't. There are two popular. This one, another one called I forgot what the name. Elliptical. Okay. You can also search over elliptical. Okay. You know. Sorry, here you can. I should put it here. So tech. Version 2 is elliptic curve. Okay, and that one's a little bit hard. Okay, so let me just make a note. Instead, another text. So you basically have elliptic curve. So you have RSA public key. So maybe I should put something like take A and B. That's better. Okay. Elliptic curve public key. Now, this one I'm not talking about. Okay, but it's there. By the way, this one is a little bit. It's actually more efficient. This one is used. This one is used for really difficult, encryption. But if you want something to be cheap, in other words, instead of storing a large prime, you want to store sort of like a small key. You use this. And that's why this one technique is computationally cheaper than RSA, hence used in IoT, Bitcoin, etc. Okay, so some of the things that I say you use you don't use RSA in some of the Bitcoin transaction because this is cheaper. In other words, it's more efficient. But but RSA is theoretical, proven, not crackable. Okay, unless you have quantum computing. This one isn't. Okay, but it's technical detail. Okay, so in practice, even though the secure way, proven mathematically and everything is RSA, there's another way that is not technically proven to have the same property, but it's, you know, in 30 years of usage, nobody has cracked it. So it's practically the same in as secure. So you talk about key size. So maybe you can search this. Key size RSA versus elliptic curve. There should be a table. Oh, it's okay. Oops. Anyway, there's a table somewhere out there that compares basically. Maybe here. That's the table. Okay, cheapsecurity.com. Cheap security. Okay, so that's a key length of RSA because elliptic curve. So it's much smaller key length of comparable level of security. Okay, so this is the RSA algorithm that you learn. Elliptic curve is another one. Okay, this one is if you go to elliptic curve cryptography arithmetic. Okay, yeah, it's this function. It's this function. I'll just draw you a picture. Elliptic curve. Okay, there it is. So this elliptic curve is very, very complicated to use. Okay, let's say you take this one. I think this is the one that's used on the internet. Okay, basically, instead of having a private key here, okay, you have something like take a secret message, okay, and then you do elliptic curve addition public key times on this, and then basically that's what this comes down to. You do some kind of elliptic curve public key times to get the message, and then decrypted message or the secret message do elliptic basically something like that. And then this is private. It looks simpler to explain, but not really. But maybe, you know, next year I would use this example instead. But elliptic addition is a bit weird. Elliptic curve addition. Okay. So that's elliptic curve. Elliptic curve cryptography. And this is RSA cryptography. Okay, so that's it. Well, I can do that. Okay, so now you understand why the emergence. So talking about this diagram that I have to say that, you know, starting kit, right? Schema, framework, starter kit, right? Okay. So this thing, cryptography, has its own starter kit, right? For example, right? So I can, in fact, I should give this as an example, right? So the technology itself has a science, and science based on mathematics and so forth. So that's why all this before World War II has encryption. So basically this tech number one, you had here, tech number one. Okay, in fact, very advanced technology by World War II. Sorry, by World War II, it's very advanced. Okay, but what is not available is sort of like a public access. So it's within military. You have to have a control chain of command. You have to be able to pass secret code book. And somebody gets caught with secret code book would have to kill himself and burn the secret book, whatever, right? You can't do that over the internet. So technology number two, you can exchange key on the internet. Number three, you can have somebody send you a secret, not knowing how to unlock because all it has is a lock. So it's a public lock, okay? So it's a one-way communication. So these two things is a technology after World War II, okay? And it has all the equation and a confluence, right? Supply, that's basically the supply is RSA and Diffie-Hellman, right? But the demand is what? The demand is the internet. The demand is internet. So timing and all that. This is an example of what I mean by emerging only happens when you have a confluence of factors. Okay. So cryptography, security, that's what we talk about today, is an example of this. Okay. You have technology. So you have to wait a while, right? You have to wait for after World War II to have this technology that's sort of like a public access to security. Normally you had only military have that kind of way of keeping secret. So you can think of up to World War II, military can keep the secret. So let's put that way. Up to World War II, the military can keep secret. Keep send secret. Okay. After, I think 1979, anyone can keep send secret. Yeah, right. Okay. Okay. Even before internet. Okay. So after 71, so basically RSA, I think, let me make sure I don't give you the wrong information. Year RSA invented. '977. Sorry, my bad. 1977. Okay, so that's the story of today. Up to World War II, military can keep and send secrets. After 1977, anyone can keep and send secret. Okay. So that's technology number one. And now, 1, 2, 3, 4. Okay. So that's what you learned about today. And after quantum computing, nobody can keep a secret, let's say. Okay. Right.